from Earth, it's Space Radio. This is Paul Sutter, and coming up, we're talking about, will James ever make it to space? Taking bets now. And of course, taking listener questions about all things in this beautiful universe, because that's what this show is about. We record every Thursday at 4 p.m. Eastern, and you can leave a voicemail at spaceradioshow.com to get your voice on the air, because I don't want it being 100% my voice. That's a little bit monotonous. And of today's Blueshift, I'll be talking about unscientific questions. But first, the news. Hello, space fans. Welcome to Space Radio. I'm Paul Sutter, astrophysicist at Ohio State, and for the next half hour, your agent of the stars. Got an exciting show for you today on Space Radio, where we talk about all things space, astronomy, astrophysics, rocketry. If it's above the Earth's atmosphere, it's in this show's universe. This show lives on listener questions. We record every Thursday at 4 p.m. Eastern. So go to spaceradioshow.com and leave a voicemail anytime. And if it's a halfway decent question, I will put it on the air and I will give you a halfway decent answer. You can also follow along on our live streams on YouTube and Twitch. That's spaceradioshow.com for the links. And you can be one of the amazing space cadets tuning in live from around the world, including Morgantown, West Virginia, Falun, Sweden, Salt Lake City, Utah, and Kempner, Texas, and more. That's spaceradioshow.com for the links. Send me questions, folks, because I've only prepped 10 minutes of show material tops. So get those calls in. Hey, Space Cadets, how you doing today? I've got a couple voicemails that I might or might not play, depending on how good your questions are. But first, I'll do some news. How about that? Well, you guys are fermenting on that. Oh, my notes. Where'd my notes go? Sorry, Greg. I was about to start. It was so good. I thought I had it. We don't want to disappoint Greg, do we, guys? Before I start taking calls, I want to share some interesting bits of news I caught recently. And James Webb Space Telescope, the successor to the Hubble Space Telescope. But I actually have a little bit of problems with the word successor right off the bat. You see, the Hubble Space Telescope, it's been up since the early 90s, and it's a telescope mainly in the visible part of the spectrum. It's for looking at stuff like your eyes would look at stuff, and it also has some infrared capabilities. The James Webb Space Telescope is not a visible light telescope. It just isn't. So it's not going to take pictures the way the Hubble has taken pictures. So I feel like NASA's like setting themselves up for a big PR nightmare, because it's like successor to the Hubble, successor to the Hubble. And then everyone's going to be like, where are the pretty pictures? And it's like, this one doesn't take pretty pictures. Period. End of sense. I will get some gorgeous images out of it, but it's an infrared telescope. It's an infrared telescope. And it was chosen to be an infrared telescope because it had a very, very specific design mission. It's trying to hunt for, among other things, the first stars and first galaxies to ever appear in the universe. And the light they've given off billions of years ago, by the time it reaches us, isn't visible light anymore. It's stretched out down into the infrared. So you need an infrared camera in order to take infrared pictures of infrared things, including the first stars and the first galaxies. This is assuming it actually makes it up into space. And I have a running joke that every time someone says the words James Webb Space Telescope, the launch gets delayed by a month. So right now we're looking at an approximate launch date of February 3rd, 2357 AD. Now, I hope I'm wrong about that, but the challenge, the big challenge, one of the big challenges with the James Webb Space Telescope is that it's a big honking telescope. And it's actually too big for a rocket. It's too wide for a rocket. So it has to be folded up to fit inside of a rocket. And then once it gets into space, it's going to unfold. If we get that part wrong, we don't get a telescope. So if like one little bit, if one's like one little folding goes off, no telescope. Zero telescope, zero images, zero pictures, infrared or otherwise, no science whatsoever. And you might be like, well, why don't we just go up into space and fix it like we did with Hubble? Remember, Hubble had a mistake. One of the mirrors was miscarved. And so we actually had to go up and put like corrective optics on the Hubble. The Hubble is in Earth orbit. It was accessible by the space shuttle. The James Webb Space Telescope is not going into orbit. It's going far, far away. It's going to something called a Lagrange point, which is a stable gravitational point very far away from the Earth in the solar system. We're not rescuing it. If we mess something up with the James Webb, that is it. Period. End of sentence. So, of course, there's going to be a lot of delays. Of course, there's going to be 1,000,001 tests, because if we get it wrong, that's it. Nobody gets a James Webb. And so it's delayed. It's over budget. I hope it actually makes it up into space, but I can also understand why it's taking a while. That's the latest and greatest when it comes to space. It's time, though, to have some questions. Ooh, Raj, is Louvois still planned? I believe it is. But I don't know too much about Louvois. I'd have to read about it more. And Niji, I like that. James Webb is more like a child of Hubble and Spitzer, only more so. I like that. It's not the successor to the Hubble. It's like a baby of Hubble and Spitzer, which Spitzer just does not get enough PR. Poor Spitzer. Sorry about the low quality. I had settings left over from a few weeks ago. Yeah, 3 weeks ago I was in Hood River, Oregon. I was doing a live show from a classroom and did the whole show. I had the streaming button turned off. I did the whole show thinking I was online and streaming out to the world, but I had the switch off. It was in testing mode because I was testing it. So all the settings are left over. I was running it from my cell phone, and as you can imagine, that wasn't turning out so well. Oh, yeah, SHM, if NASA isn't going to launch the James Webb, can you just get it like for your room? So you might need a pretty big room. Like, it's a large object. So if you're thinking as like a centerpiece or, like a statement piece in like a foyer or something, not really going to work. And if you've always wanted to have a telescope in your room, you could just, have you tried buying a telescope and putting it in your room? I mean, I'm just saying, don't let your dreams be dreams. All right, let's do some questions. I think I'll start this segment with a voicemail and then let you guys collect some more questions. All right, we've got a question ready to go. And remember, you can join the conversation by going to spaceradioshow.com and dropping a voicemail. And, I'm so excited for this question. Greg, play the tape.
Hello, Paul. What would happen if two black holes of equal mass merged, but one was made of matter and the other was made of antimatter? Thanks for your time and keep up the awesome work you're doing. Regards, Pete Ellinger, Sheffield, UK.
All right, great question, Pete, and thank you very much for the kudos. So this is a very interesting question that really gets into the heart of actually a huge mystery when it comes to black holes. So your question was like, if I got one black hole and I created it out of matter, and I got another black hole and I created it out of antimatter, and I smashed them together, what would happen? Now, if I smash regular matter and a ball of matter and a ball of antimatter together, there's going to be a big boom. There's going to be a lot of energy released. So you might think that, if I make a black hole out of matter and I make a black hole out of antimatter and smash them together, it might be a big boom. There isn't. There isn't going to be a big boom. Black holes don't care what they're made out of. If I have two black holes and I make one out of matter and I make the other out of antimatter, and they have the exact same mass, they're identical. They're identical. Which means I can take my matter black hole, the black hole I made out of matter, and I can take the black hole I made out of antimatter, and I can close my eyes, and then you can shuffle them around, and then I open my eyes, and I try to guess which one is which. I don't know. If they have the exact same mass, they are identical. It doesn't matter what goes into a black hole. Black holes are very, very simple. And there's this very intriguing connection. There's only 3 numbers you need to explain a black hole, or to completely and totally characterize a black hole. You need to know its mass, you need to know its charge, and you need to know its spin. If you have those 3 numbers, you have everything you need to know about a black hole. Does that remind you about anything else in the universe? I can't hear what you're saying, so I'm going to go ahead and guess that you said particles. And you are right. Fundamental particles are characterized by just a few numbers. Like an electron has a mass, has a spin, and a charge. Boom, done. That's how I define an electron. Black holes are defined by 3 very simple numbers. Subatomic particles are defined by, a small set of very simple numbers. Is there a connection here? We don't know. Is there something cooler going on? We honestly don't know. I just thought I'd bring that up just so you can ponder that tonight. Now, the big mystery about black holes is that this gets into the whole black hole information paradox. Basically, the question is, all this information goes into a black hole. Like you make one black hole out of matter and another black hole out of antimatter. But then the black holes are identical. But then black holes evaporate because of Hawking radiation. They eventually disappear. So what happened to all that information? Information, as far as we can tell, isn't created or destroyed in our universe. It just gets mixed up. But it looks like that fundamentally destroys information. What's going on? We don't know. This is why it's called a paradox. There's something going wrong with black holes. There's something fundamental that we just do not understand about black holes. And your question, Pete, gets right to it. One black hole made out of matter, another black hole made out of antimatter. You can't tell the difference. And that seems fishy. That seems wrong. That seems like it shouldn't be, because we should be able to tell which black hole is different because we made them out of different stuff. But we can't. So what happens to all that information? What happens? If you have an answer, please let me know, because it's kind of a major problem in modern physics that we have no good solution for, or really any solution for. Thank you for that awesome question, Pete. We're going to take a quick break. Don't forget to leave a voicemail at spaceradioshow.com, and you can get your voice just like Pete, which Pete had a very lovely radio voice. Thank you for that awesome message, Pete. You can also catch the live streams every Thursday at 4 p.m. Eastern on YouTube and Twitch. Just go to spaceradioshow.com for the links, and you can join the always awesome Space Cadets. I'm Paul Sutter. This is Space Radio. This show is brought to you by you. Go to patreon.com/PM Sutter. That's PMSUTTER. And you can learn how you can keep this show happen for as little as $1 a month, as much as an infinity dollars per month. That's right, unbounded at the top. And we'll see you after the break. That was an awesome question, Pete. Thank you so much. All right, and there are lots of Space Cadet questions for the second half. Ooh, fun questions. All right, Space Cadets, it's your turn. Gotta uncross my legs. I'm starting to fall asleep. Yeah, so as you can tell, I'm not in... Unless Studio A of WCBE Radio got a major overhaul. I'm not there. I'm traveling as usual. So Greg's not even watching, folks. It's just you and me, Space Cadets. He'll catch up though. So this is the thing. So I can make fun of him, and he can't even look at me. He can't raise his eyebrows. He can't roll his eyes. He can't shrug. He can't agree with me. Sometimes I don't think you guys know this. Sometimes when I make fun of Greg, he just nods his head like, "Yeah, fair point, fair point." He does that sometimes. If someone offered me an infinity of their dollars, I would turn them down as a courtesy. No, I would accept. I'd split it with them. You know why? Because half of infinity is still infinity. So you can give me infinity dollars, I'll give half back to you, and we both have infinity dollars. That's the magic of infinity. Ooh, yeah. Add Raj, add a repair drone to the James Webb. I feel like we would have no idea how to do that right, but that sounds like such a cool idea. All right. Second segment, Greg. You ready to go? Doesn't matter. Welcome back, everyone. I'm Paul Sutter, and this is Space Radio. We've got tons of Space Cadet questions ready to go. But remember, you can join the conversation by leaving a voicemail at spaceradioshow.com or by joining the Space Cadets over at YouTube and Twitch. That's spaceradioshow.com for the links. And getting us started today, we've got SAHM on YouTube asking, do telescopes have to collect and store data, or do they just reflect the radio waves back to Earth? Like what's the process when we've got these space telescopes going on? So very, very, very rarely will a space telescope actually handle a lot of data, a lot of information that it acquires. Why? Because that requires storage space. That means hard drives. That means just bulk that could be better used towards, say, a giant mirror or camera or electronics. The space telescopes act as relays. The information comes in, like the light comes in, whether it's radio waves or visible light or infrared or anything, comes in, hits detectors, which detectors are basically very fancy digital cameras. And then that information gets beamed back down to Earth, a bunch of ones and zeros. So the space telescope is doing the work of taking a picture. It's like sending your smartphone camera into space. It's going to take the picture, and then it's going to call you up on the phone and say, "Okay, here's what I got today." This is exactly how we operate not just space telescopes, but even ground-based telescopes all around the world. They are processors of the information, and then they send that processed information out to whoever's interested. Goran over on YouTube is asking, how come we get a redshift blueshift when the light speed is constant, regardless of how the light emitting object is moving? So you're absolutely right. If I'm moving or if I'm staying still, I'm emitting light. The light is coming off of me. I'm glowing in light at the speed of light. If I start moving, light is still coming off of me at the speed of light. Light travels at the speed of light, period. No matter how fast you're moving, when you're sending it or receiving it, the speed of light is always, always, always the same. But that's exactly why it redshifts and blueshifts. Because if I'm moving and I spit out some light, that light has some extra energy because I'm moving. It has its energy from the light, plus it has my kinetic energy from moving. So, but it can't go faster because it can only go the speed of light. So instead, that energy goes into blue shifting it and shifting it up to higher frequencies, higher frequency, higher energy light. And the exact opposite happens if I'm emitting light behind me. If I'm moving really fast and I shoot light out behind me, then I'm pulling energy away from that light, but it can't go any slower. The energy has to go somewhere. The energy has to come from somewhere. So it comes from its frequency, and it will get redshifted to longer frequencies, lower energy frequencies. So it's the very fact that light can only go the speed of light that you get this whole redshift, blueshift thing. Another question over on Twitch from Campbell Duncan is asking, in a recent Ask a Spaceman, which is my podcast, by the way, askaspaceman.com, I talked about particle wave duality, this fundamental concept in quantum mechanics, which is, man, if you want a headache, just start thinking about particle wave duality. It's like guaranteed migraine material. Campbell's asking, is that related to how you say it's not about the particles, it's about the fields associated with it? Yeah, so I want to be, there's this, evolution in thought that happened in the 20th century, where first we figured out quantum mechanics, which is all this particle waves and superposition and all the good stuff of quantum mechanics. And then we figured out an upgrade to it, something called quantum field theory. And quantum field theory doesn't talk about waves. It doesn't talk about particles. It just talks about fields. Just talks about fields, where every particle in the universe, or every kind of particle, has a field associated with it. And this field permeates all of space and time. And then little chunks of that field are what we call the particles, and sometimes there's little wiggles on that field, which is what we call the waves. So that's like an upgrade. It still includes this whole particle wave duality thing, but with an extra layer of interpretation on it. And if it seems hard to keep straight, it's because it is. Over on YouTube, Thunderduck is asking, what do you think about the Fermi paradox? Are we really alone? Well, I suppose there's a difference between being alone and being lonely. And so, but it's a good question. It's a good question. As far as we know, right now, as of today's date, whatever it is, June something or other, 2019, we have absolutely no evidence for any life, intelligent or otherwise, outside the Earth. Period. That's it. That's all we got. We have no evidence for any other kind of life except for our own. Until we have evidence for it, we have to assume that we are alone. I can guess, I personally think we're not alone. There's probably other life out there. There's probably other intelligent species out there, but we have no evidence for it, so I can't say it. I can only guess. And the whole deal with the Fermi paradox thing is that, okay, if life happened here, that means life is common in the universe because we shouldn't be very, very rare. But if life is common in the universe, then where is everybody? We're all alone. But you say, okay, well, life is rare, but then why is life not rare, not common enough that we don't see it everywhere, but not so rare that there's basically no life at all in the universe? Like, why do we seem to be so special? Why do we seem to be so unique? Why do we seem, different? We don't know. That's the heart of the Fermi paradox, is that whatever causes life in the universe is extremely rare, but not so rare that it's impossible. And that's a very, very awkward setup. So, what's the answer? Well, we'll just have to think about it more. Maybe if we find somebody else and we can talk to them about it and we can get some resolution to the Fermi paradox. SAHM on YouTube is asking if I have a postdoc position for you. Sorry, I'm not hiring postdoctoral researchers at the moment. But if you're curious, by the way, if you want to dig into the bowels of the astronomy world, go to something called the Astro Rumor Mill. The Astro Rumor Mill every year posts every single open academic position in astronomy. And it's a single webpage. Let that sink in. you can fit every single open position around the world in astronomy in a single web page. It gets updated every year because every fall, all of astronomy and physics shuts down when all the junior researchers are busy applying for jobs and all the senior researchers are busy reviewing those applications. So for about a solid 3 months from like November, December, and January, no research happens around the world because everyone's trying to either apply for jobs or select candidates for a job. And all those jobs are listed on a single website. Thank you, everyone, for all those amazing questions. Oh, the Space Cadets are so much fun. We're almost out of time today on Space Radio, but before we go, it's time for the Blue Shift. Is dark energy a quantum unit of space-time? We think dark energy might be a property of the vacuum, but we're just not sure. Oh, thank you, Nancy, for putting up the link to the Astro Rumor Mill. So if you're outside the field, the Astro Rumor Mill is like really fun because it gives you a peek into what kind of jobs are open, who's competing for them, who's top ranked, who's shortlisted, who got the job. If you're inside the field and you're actually doing this, that rumor mill is one of the most toxic things imaginable because right there on a single web page, you are seeing who your competition is. You are seeing who who is shortlisted for the same position, who ended up getting it, but then accepting or rejecting it. I'm telling you about the rumor mill, like almost like as a curiosity, like outside the field. Inside the field, I think it's one of the worst possible things. It's just because it just drives you insane. I used the rumor mill for my first postdoc. I was obsessed over it. Ever since, I've never even looked at it because it just destroys you as a human being. It's not right. I'm Paul Sutter, and you're listening to Space Radio, and this is the Blue Shift, my opportunity to get a little bit closer to you. And I want to talk about unscientific questions. There are some people, and I'm not going to name names, mostly because I can't think of any names off the top of my head. There are some people that claim that science can answer every question, that every question that's brought to humanity's consciousness can be answered by the scientific method, and that the scientific method is the superior way to answer some of these very fundamental questions. Of course, I disagree with that. And I disagree with that even though I'm a scientist. But as a scientist, I know that science isn't fully equipped to answer every kind of question. We just have to get used to that. We have to accept that. Science is an incredibly powerful tool to answer some kinds of questions related to how the physical world works. We're like really, really good at that. Look at the past 400 years of us figuring stuff out. Like, man, we've come up with a lot of answers. We should be proud of ourselves. Of course, there's lots of mysteries, but that's just job security. But there's lots of questions that science fundamentally can't answer. Questions about like ethics. How do you answer an ethical question with the scientific method? You don't. You have to tackle it with some other method. But what I think is even more pernicious than that is questions that seem like they should be able to be answered by science, but science has a really, really bad job of doing it because, say, the data are really noisy, or an effect is too small, or you can't really design a good, robust, controlled experiment. Like, there are questions that come up in, say, like how to organize societies, or how to have systems of politics or governance or justice or economics. And it seems like, I see this phrase a lot, like evidence-based thinking, evidence-based policy. And to me, that actually raises some alarm bells because the evidence doesn't always tell you what the right answer is. And you can't always gather the evidence. You can't know. Like how can you decide like a policy decision? Are you going to like split the country in half and like half the country gets policy A and the other half gets policy B, and then, half the country like suffers for a decade and the other does really well, so you learn you learn from that experiment and then you can apply the policy. Like you just kind of can't do that all the time. So I always try to be cautious when it comes to evidence-based thinking, because scientific method, evidence-based, it's not always the answer. And unfortunately, this broadcast is almost done. I do have an answer for that. Thank you for joining me on this voyage of space radio. Once again, I'm Paul Sutter, and this show is brought to you by the Ohio State University Department of Astronomy. Learn more at astronomy.osu.edu. This show is also brought to you by, guess who? You. You could have guessed that. Go to patreon.com/PMSutter to learn how you can contribute and keep this show going. Thanks to Greg Moebius for producing, Nancy Graziano for wrangling the Space Cadets, Dan Michalko for being awesome, and all the fine crew at WCBE Radio for making this show possible. We record every Thursday at 4 p.m. Eastern. You can leave a voicemail at spaceradioshow.com. You can also join the Space Cadets in the live stream on YouTube and Twitch. Go to spaceradioshow.com for all the links. And of course, thanks again, Earthlings, for listening. See you next week. And remember, science is for sharing. End transmission. Sorry, Nancy, that Nightbot isn't working out for you. I'll look into it. I got a tab open. I turned it back on, but I guess it just didn't work. Oh, Sopwith, that's cool that you've had conversations about that. Yeah, I feel like these kinds of thoughts just started percolating in my brain about evidence-based policy and evidence-based decision making. I just started percolating like a week or so ago, and I definitely have some more thinking about it. So you're getting some really raw, unfiltered thoughts. Like they're not even fully formed yet. Thank you. Next week, we are going to do a live show, but it's going to be 4 p.m. Pacific time. So it'll be 7 p.m. Eastern. It's going to be live. We're having our AstroTour Star Party at Joshua Tree. So there's going to be a live audience. We're doing 4 p.m. Pacific. But we will be live next week. And I will see you then. Thanks, everyone.